Hey guys, welcome back. We're finishing up confidence intervals. We're going to do a bit of a review here before I give you guys a practice test on Friday, and we'll take the quiz over confidence intervals the first day we come back. So there's a few things that are new on this one that you'll need to see how we put things in the calculator. So do make sure you watch the video. And let's start out with a bit of a review. So we're talking about color blindness on number 2, and these problems are actually from the chapter or the unit review, not from chapter 18. So if you're looking for the questions in the textbook, it'll be on page 594 or something like that, and the answers in the back of the book will be under the Unit 5 review, not under Chapter 18. Okay, so now we clear that up. All right, so we're looking at color blindness. So for somebody who has red-green color blindness, this would be the image they see when it's actually in fall, and this is what we would actually see in normal vision, so they're not picking up the differences between those frequencies. All right, so number 2 says that medical literature says about 8% of males are colorblind. So what's unique about this question is that we know the true proportion. We believe it's about 8%. So if we assume that the true proportion is 8%, so that's like the population is like the whole pot. So of all the people in the world, 8% of males are colorblind. So that would be like knowing from the manufacturer what percent of all yellow M&Ms, or what percent of all M&Ms are yellow. Let's say it's 8% or something like that. It's very rare that we actually know the true proportion. It's usually that it's some value like the C-fans that's always constantly changing, not some set number. But in this case, if we're building sampling distribution models, they're going to be built around the true population proportion, which we rarely ever know. Not instead, what we usually do is we usually base it on samples. So whatever sample we have, even if it's a random sample of thousands of M&Ms or something like that, we can get pretty close to narrowing it to what the true proportion is. But to actually know the true proportion, that's really, really rare. So normally we build confidence intervals off of samples, but sampling distribution models, which is what the whole idea of a confidence interval is based upon, is whenever we know the true proportion. So there's a slight distinction between what we did in chapter 17 and what we're doing in chapter 18 with confidence intervals. Confidence intervals are based upon samples, which is the next best thing we have, right? And we have where we have the margin of error on both sides, but the actual population of 8% would be the foundation of a sampling distribution model. So the sampling distribution model is the distribution of all possible samples of a certain sample size. So in this case, if we have in a large lecture hall, 325 males, if the true proportion is 8%, then what would a random sample of 325 males be? Well, it would be centered at 8%, but we know there's going to be variation from sample to sample. If we go to another sample of 325, it's going to maybe have slightly more than 8%, and maybe another one would be slightly less than 8%, right? And so the actual sampling distribution model really comes from the binomial, right? So the binomial, it's success or failure, whether or not you're colorblind, just like finding a blood type or something like that. And so if we do a sample size, let's start out with 10, then our distribution is going to be skewed, right? So it's going to be skewed to the right because our sample was not large enough to give us guaranteed 3 standard deviations that are unobstructed. So remember, we have to expect at least 10 successes and at least 10 failures. So with a proportion of 8%, to find out the smallest sample size we could have, we would do 10 divided by 0.08, our probability of success, which would mean 125. So even if I had a sample size of 81, which I'm using specifically for a reason, even though it looks like we're good enough, guaranteed 3 standard deviations, in fact, each standard deviation is 2.4, so 2.4 times 3, good question. I can actually do that if I want to. So 2.442 times 3, which means we have to have a mean of greater than 7.3, and we actually have an expected value of 6.48. So almost 3 standard deviations. But instead of having to do that rule for each one of them, we just have a general rule of expecting at least 10 successes, and we're not. Our mean is less than 10, so in this case we're not going to be able to use it, but that's okay. So what size of a sample would be good enough? Well, if we increase it to 100, 10 wasn't enough, right? We increased it to 50, and now it looks more nearly normal, but still it's cut off on the left bound, so that wouldn't be good enough. 100, still not expecting at least 10, so technically we probably can use it, but we're not going to. So it's not until we get to a sample size of 125 that we would have expecting at least 10 successes, and that's what we have here. So if we have a sample size of 325, certainly we're expecting at least 10 successes and 10 failures, because we're expecting to find at least 26 on average successes, people who are colorblind. Okay, so now that we've got that out of the way, just notice the difference between when we actually know the true proportion, which is very rare that we know the population. Usually we're basing it off samples with confidence intervals, but in this case we would expect 68% of samples to vary within 1.5% of the 8%, which would go from to 9.5 down to 6.5. All right, so that would be what we consider a typical one, would be going 2 standard deviations, which would be 3%. So we would expect basically 95% or 2 standard deviations of all of our samples of 325 to be within 3%, which would go up to 11 and then all the way down to 5. So between 5% and 11% of the 325 people to be colorblind, which is a pretty large margin of error if you think about it, if we're adding and subtracting 5% or 3% from both sides. All right, so if we had a sampling distribution model, which it is, and we do samples of 81, this is the standard deviation we would expect. This would be the binomial model, a standard deviation of 3%. You can find that by doing P times Q. Instead of the square root of P times Q times N, we're going to do P times Q divided by N under the square root. Remember, we just divided everything by N. So instead of having 6, it would be 6 divided by 81, which is going to give us these percentages that we have here. Okay, so basically everything in the binomial was just divided by N to change and convert it or scale it down back to proportions in this case. All right, so this would not work because we're not expecting at least tens, but if we quadruple the sample size, which is why I picked 81, quadrupling the sample size would be now 325 roughly. And so now if you notice what happened to our standard deviation, now our standard deviation is 1.5 instead of 3, so it's exactly half of the standard deviation. So what happens whenever we quadruple our sample sizes, it cuts our standard deviation in half, which is absolutely fascinating. So I just want to show that to you one more time. So that's the inverse or the reciprocal square root law, which is the same law that we apply to gravity. So as you get 4 times as far away, your gravitational pull will be cut in half. So if you are 4 times the radius of the Earth away from the radius of the Earth, then you will weigh exactly half as much as you weigh on the surface of the Earth, which is exactly how that works. Yes, thank you, physics. But at some point, you'll also have the gravitational pull of other planets, including the moon, which will actually, just like the tides, will pull you away and make you weigh less than you would if you were on the other side in the moon. Anyway, kind of cool, fun stuff, right? Just literally NASA, you know. All right, colorblind. Would we expect the sampling distribution model to be more nearly normal? Yes, because by the time we have a sample of 325, 8% of that's 26, which is greater than 10. So we have at least 10 successes and 10 failures, so we're guaranteed it's not going to be cut off by at least 3 standard deviations from the hard left bound of 0 or the hard right bound of N. So yes, that would be good to go. Because of central limit theorem, all distributions, regardless if they're binomial, which ours are for proportions, or if they're unimodal or skewed or anything like that, multimodal, all of them will eventually end up turning into bell curves, which is fascinating. That's the central limit of all of, or the central limit theorem, or the central idea of all statistics, is that all samples, from regardless of the shape of the proportion, as we increase the sample size, will turn into bell curves, which is fascinating. All right, so what is the sampling distribution model? Centered at 8%. Again, this is because we have the true population portion we believe is 8%, with samples of 325. So we find the standard deviation, the mean is going to be centered at 8%. Okay, the standard deviation, we just put that in the calculator. So that's going to be 0.08 times 0.92, so probability of success times probability of failure, divided by our sample size of N, and then we want to take the square root of all that stuff. So caret 0.5, which is where I got basically the 0.15. So put that in the calculator, and we get basically 1.5%. All right, so you can go ahead and fill in and sketch the model. So centered at 8% with a standard deviation of 1.5%. So just model that going in both directions. So this is the sampling distribution model is also a normal model. So that's why we're using the capital N to denote that this is a normal model centered at 8% with a standard deviation of 0.015. So that is our sampling distribution model of 8% for sample sizes of 325. All right, cool stuff. Next question, birthdays. All right, during a 2-month period in 2002, 72 babies were born at Tompkins Community Hospital in upstate New York. The table shows how many babies are born on each day of the week. If births were uniformly distributed across all days of the week, which means, well, we'll get to that in a little bit, then how many would you expect on each day? Well, there's 7 days in the week, and if it was completely independent of the day of the week, which day that you were going to deliver on, then we would expect to be 1/7 of all of those to be on each day, right? So a seventh of, basically the proportion that we're going to be doing is 1/7. So we can put that in the calculator if you're curious. So we would expect 14.3% of all the births to happen on any given day. All right. Only 7 births occurred on a Monday. Okay, well, what is 7? What is 7 out of 72? So that's the question we have. So 7 divided by 72, because we're going to be dealing with proportions in this thing. Instead of doing a binomial with expected amounts, we're going to convert everything to proportions, because that's what we're doing for this unit. All right, so 9.7%. So 9.7% out of our sampling distribution model, is that considered unusual? So is that more than 2 standard deviations away from the mean? That would be what we would be considering unusual. So what is our sampling distribution model? Well, a sampling distribution model is going to be centered at the true proportion, which is 1/7, with a standard deviation of, for sampling distribution model, sample size of 72. And this is, again, because we have a sampling distribution model, because we know the true percentage. It's just like a model from dice or from cards or from flipping a coin. We know it has to be 50-50. In this case, we know it has to be 1 out of 7, would be if it was actually uniformly distributed. All right, so that's why we can do the sampling distribution model in that case. So it's centered at 1/7 with a standard deviation. We're going to do 1/7, which is probability of success times probability of failure, which would be 6/7 if you think about it. And then I'm going to divide all of that by our sample size, n of 72, and then I have to take the square root of that, so half power, which is basically going to be 4.1 if I round. All right, so I'm going to go towards the low end, so fill in those values there, which you know how, just subtract it from the 1/7. And then what we're going to know is where would it be, where would 1/7, or where would 7 out of 72 show up? So 7 out of 72, I think I did that before, which was 9.7%. So where was 9.7% on that whole thing? So it's slightly more than 1 standard deviation below the mean, but would not be considered unusual because it's not less than 6.1%, which would be 2 standard deviations below the mean. So to find the area under the curve, to find out what the probability of that actually occurring, forgot to lock this in place apparently. To find that probability, we use the normal CDF, because this is a normal model. So I'm going to use the normal CDF. So second distribution under variables, normal CDF is the second option here. Our lower limit, we could technically do 0 because we can't have a percentage less than 0, right? Our upper limit, we're doing 9.7%, but I'm going to be exact and do 7 divided by 72, because it was 7 out of 72 bursts. Centered at our mean, which I'm going to be exact on this one as well because I can, which should be 1/7, right? With a standard deviation. This one I am going to round because I'm lazy and I don't want to put in that entire formula again. And yes, okay, that is correct. All right, then hit paste, and that'll give us a probability of 13.3%, so 13.3. And so this is what I put in the calculator, going from 0 to 7 out of 72, which is this percent we have here, centered at 1/7 with a standard deviation, which was rounded here. Okay, cool. And 13.3 if you want to round, or 13.26. going around that way. All right, part C. There are 17 bursts that we saw on Tuesday, which is the most that we had on any given day. Is that unusually high? So now for unusually high, instead of being unusually low, it's going to be unusually high. So we want to see if it's beyond 2 standard deviations in the other direction. It's still the same sampling distribution model. We just add this time to go to the right side. And all we have to do is find out what that fraction is. So what is 17 out of 72, which is going to be 23.6. So where's 23.6 going to be? Well, it is above 2 standard deviations, so it would be considered unusual. To find the area under the curve going up to it, we use the normal CDF to find out how unusual it is. But even at this point, we would be able to say it's unusual because it's more than 2 standard deviations away from the mean. All right, so to find the exact value for that, we'll go to second distribution normal CDF. My lower limit is going to be the 17 out of 72. The upper limit, I'm going to go all the way up to 1 because we're doing probabilities, and the large probability you can have would be 1, right? Centered, that's all the exact same, and this is for the sampling distribution model, which would be 1.15%. So basically 1.15, okay, and that's what I put in the calculator. Left bound was 17 out of 72, right bound was 100%, centered at 1/7, and our standard deviation was rounded. Okay, cool. So that would be very rare. It's almost in the top 1% of samples, and so we would be able to reject that and say there's definitely something going on. This did not occur by chance. And so what's happening is that these are not natural bursts. So maybe if this data was collected before we did epidurals or before we induced, before we did cesareans and stuff like that, a lot of times people are actually scheduling the days that their children are born. They're not being born at home. Like I was born at home, but I don't know, did my mom have an epidural? I'll have to ask. Did it just happen, or did they rush it, or was the baby too small and so you get what I'm saying, or is the baby too big and so they induced early, stuff like that. So there's a lot of things that happen. It's not just randomly chosen. So unfortunately what ends up happening is you end up having days that it's more convenient for the clinic to do their bursts, and so they'll do all their bursts or all their cesareans and stuff on certain days, and they won't do them on others. So that's why it's not evenly distributed. There's something else going on there. All right, number 9, net newsers. In June of 2008, the Pew Research Foundation sampled 3,615 U.S. adults and asked about their choice of news sources. They identified 13% as net newsers who regularly got their news from online sources rather than TV or newspapers. Okay. Pew reports a margin of error of 2% for the result. What does the margin of error mean? Well, the margin of error is from our confidence interval, and it's what we're going to add and subtract to both sides of our sample proportion. So they thought 13%. So their sample said 13%. But we know it's not going to be exactly 13%. We have to have a range of values here. And so they believe that the true proportion is within 2% of the 13%, 95% of the time or something like that, whatever their confidence interval. So they believe the true proportion is within 2% of our sample statistic, which was a 13%, with some probably 95% degree of certainty. So 95% of samples or confidence intervals would successfully capture the true proportion within 2% of our sample statistic, because the sample statistic is what's going to vary. If we do it again, maybe they thought it was 14, and then maybe we do it again, maybe we thought it was 12. But if we add it, that's where the margin of error comes in, because in the long run, 2%, 95% of all confidence intervals created from this method or whatever will successfully capture the true proportion within the margin of error. Okay. Pew's survey included 2,802 respondents contacted by landline and 813 contacted by cell phone. If the percentage of net newsers is the same in both groups, Pew Research estimated the percentages separately, what group would have the larger margin of error? Well, the only difference we see is that in the sample size. And so if we have a larger sample, that's going, as we quadruple, every time we quadruple the sample size, that's going to cut our margin of error in half. And so if this is a fourth of this one, then it's going to have double the margin of error. So smaller samples have more variation. We see that even with coin flips, right? So if we flip a coin 10 times, having 8 out of 10 heads is not unusual, but having 80 out of 100 heads would be incredibly unusual. So as we increase our sample size, the the margin of error is going to shrink. Our standard deviation, our standard error is going to shrink. Therefore, our margin of error will shrink as well. All right, so our explanation is those contacted by cell phone, the 813, because smaller samples vary more. They have more variation. Pew reports that 82% of the 470 net newsers they got in their survey get their news during the course of the day. So during the day instead of in the evening, I suppose. So while they're at work or at school, I guess. Far more than other respondents. Find a 95% confidence interval for that statistic. So to find a confidence interval, which you'll be asked to do on the quiz, of course, we want to go to stat, arrow over to test, towards the bottom, 1 proportion z test. It's a z, or 1 proportion z interval. It's a z interval because it's based on z scores, because this is all based on a bell curve. They say 82% of the 470. So the n is going to be 470, but the x is the number, not the proportion. They gave us a proportion. So what we need to do is 0.82 times 470. And this is where it's different, so we need to know how to do it. Now, when we do that, we can't have 0.4 of a person. So what we need to do is this value is actually rounded, and so we need to round it down in this case. So that's going to be 384. And then I'm going to delete the decimals. And if you don't change the decimals, you'll get an error, and you'll have to go back. Okay, so confidence level, they want to do 0.95, and then hit calculate. So if you see our sample proportion of 82%, it was actually really 81.7 would be the closest, right? And they rounded it up to 82%, and that's why, yeah, because it's going to be given to us as a decimal. All right, so there's our confidence interval, and I just copy it down here. All right, so there's our confidence interval, part D. How does the margin of error of your confidence interval compare with the values of parts A and B? Well, on A, we had a margin of error of 2%. On B, we are going to have a larger margin of error because we've got a smaller sample. Instead of 3,615, we broke it down to 2,802 or 813. Well, now we're even smaller sample of 470, so our margin of error is going to keep getting larger and larger. So how's the margin of error compare? It's going to be even larger because it's a smaller sample. So the largest margin of error due to the smallest sample size. Number 12, vitamin D in 2012. In 2012, the American Journal of Clinical Nutrition reported that 31% of Australian adults over the age of 25 have a vitamin D deficiency. The data came from a ASDIAB study of 11,218 Australians. So does the data meet the assumptions necessary for inference? Well, first of all, do we know the actual true proportion of all Australian adults who have vitamin D deficiencies? No, it's not like the manufacturer of the M&Ms that knows the actual true proportion because they set that thing. This is a number that's like the CFANS. It's going to be constantly changing. There might be times when, for certain reasons, there's more vitamin D deficiency that we're seeing than in other times. Or certain generations, it might be worse than other generations. It's going to change. All right, so the best that they can do is from our sample create with a margin of error, create a confidence interval. With such a large sample of 11,000, there's a good chance we've honed it in pretty close. So maybe we have a margin of error plus or minus 1%. We'll see. All right, so plausible independence. In order for us, we got to check our assumptions. So is each person going to be independent of the next one? Well, people are going to be related to each other. It is going to be genetic, so it is going to run and stuff like that. But it shouldn't really create an issue. We're just going to say that we believe each person should be independent of each other, as long as you're not and you're not going to have 11,000 people who are all related, so you should be fine. Random sampling, they didn't tell us how they gathered the information, so that's something that we would want to know. Was it a random sample? Did they only look at people from one city? Was it a convenience sample? It should be a simple random sample of people from all over Australia. Best case scenario, right? 10%. All right, we're sampling certainly less than 10% of all Australians, so even though we're sampling without replacement, we can override that because the probabilities are going to change by so small it won't change our overall conclusions. Success failure, we're clearly going to have at least 10 people who have a vitamin D deficiency and 10 people who don't, so it's large enough that it will be a bell curve. Create a 95% confidence interval, so we're going to put this in our calculator. So again, we're going to go to stat, arrow to the right to calculate, towards the bottom, 1 proportion z interval, We're going to do, they gave us a proportion, so 31% times 11,218, and then that's a rounded number, so we need to go ahead and we need to round it up because we can't have a decimal of a person, right? You don't have 0.58 of a person, no matter how much you don't like them, they're still a whole person. All right, so I'm going to round it up, and then the total number was out of 11,218, 95% confidence, so hit calculate. So I'm just going to copy that down. It's kind of fun because I can do that so you can still see what was on the screen even though I took it away. All right, so create a 95% confidence interval. There we go. It's just between those two, and I kind of did a little bit of rounding, and I always state what your confidence level is. That's just good stats. Interpret the interval in its context. So we believe the true proportion of Australian adults with vitamin D deficiency is between these two percentages, 95%. We're 95% confident. All right, so we're 95% confident the true proportion of Australian adults who have vitamin D deficiency is between those two percentages. Explain what 95% confidence means. Okay, so that means 95% of the time the true proportion will be within the margin of error, or will be successfully captured between in our confidence interval. So 95% of samples of this size will successfully capture the true proportion. All right. 14. Occupy Wall Street. In 2011, the Occupy Wall Street movement protested the concentration of wealth and power in the United States. I bet 2011, I bet you guys probably don't even remember that, but I was a junior in high school, the same school you guys are going to, at Pup City, when this happened. All right, a 2012 study at the University of Delaware asked a random sample of 901 American adults whether they agreed or disagreed with the following statement. The Occupy Wall Street protesters offered new insights on social issues. Of those asked, 59.9% said they strongly or somewhat agreed with the statement. We want to know, we know that if we ask the entire population, so if we did a census and asked the entire population of American adults, we would not find exactly the same as our sample, because the sample is going to vary. It'll be centered in a sampling distribution model, centered around the true proportion, but we still don't know where the true proportion is. That's why we create confidence intervals. So we know it's not going to be exactly what our sample proportion was. That's why we have a margin of error, the plus or minus 2% or whatever we have. Construct a 95% confidence interval for the true percentage of American adults who agree with the statement. All right, so same thing as we did before. We're going to go to stat or test, one proportion Z interval, and they're saying 0.599 times 901 that they sampled. And again, that was a rounded value, so we need to round it up. So that's going to be 540. So basically, they found 540 out of 901 people, and they wanted 95% confidence. All right, so there we go. And there's our confidence interval with 95% confidence, and that's all they asked us to do. Number 20. Enough eggs. So this is how many hens do they need to collect data on. So what should our sample size be on this one? So one of the important issues for poultry farmers is the production rate, the percentage of days on which a given hen actually lays an egg. Ideally, it would be 100%, meaning that they lay an egg every day. But realistically, hens tend to lay eggs about 3 out of every 4 days. ISA Babic, I guess, wants to advertise the production rate for the B300 layer as a 95% confidence interval within the margin of error of 2%. So if they want to be able to give the confidence interval with 95% confidence within a margin of error of 2%, then what sample size would they need to be able to accomplish that? So margin of error of 2%, so 0.02, is equal to the critical value, which if it's 95% confidence, our critical value is 1.96. And then our standard error is going to be p hat times q hat divided by n, which in this case, they believe that it's going to be 3 out of every 4 days, which is 75% probability that they will successfully lay an egg on any given day. So the probability that they don't would be 25%, which is 1 out of 4 days, and then divided by our n, which the n is what we're trying to solve for. So we got to get the n by itself, but it's got this in front of it and it's trapped under the square root, so we got to do our math, right? So we divide both sides by the 1.96. I'm going to go ahead and put that in the calculator real quick. So 0.02 divided by 1.96. Okay, and then after we do that, we're going to end up squaring both sides. So I'm going to go ahead and square it. All right, and then after we square it, we're going to switch the order of these two. So basically, we're going to divide that over here, and that's going to give us n. So I need to do 0.75 times 0.25 divided by that, which was the previous answer squared. Okay, cool. And that's going to mean that we're going to need to survey or collect data on 1,801 hens. So that's pretty large sample, but if they want to be able to find it, the true proportion within a margin of error of 2%, then that's what they're going to have to do. And so now they need to go back and either decide whether, well, do they have the money to do it, or are they going to compromise by changing their confidence level to maybe 90%, or are allowing a larger margin of error of plus or minus 3% instead of 2%, and then we can redo our data and analyze that stuff. Okay, so that's it. It went a little bit long, but we were also kind of reviewing as we went, if you notice, as we were doing the assignment. So kind of try to like actually listen and watch all of it if you actually can. That'll be a really good review for you. And then we've got our practice test that I'll be giving out on Friday, or practice quiz, and then we'll take the quiz the first day we come back. So whether that's on a Tuesday or if that's on the Thursday that I'll see you after Snowmageddon. So next week. I'll see you guys. If you have any questions, please let me know.